I'm Adyasha Mohanty, a PhD student working with Professor Grace Cow in the NAV lab at Stanford University. I'll be presenting learning GNSS positioning corrections for smartphones using graph convolution neural networks. We are currently living in the new era of Android positioning, where advances in GNSS and smartphone technology have enabled applications such as precise mapping, lane-level positioning, and augmented and mixed reality. In fact, our smartphones comprise about 1.5 billion GNSS receivers that are currently manufactured in the world. What are some of the challenges that these smartphone receivers face? Well, unlike commercially available receivers, they have higher noise and lower signal levels, which limits the positioning accuracy to about 5 meters in normal and urban environment, and this gets much worse if we talk about dense cities such as San Francisco and Chicago. We can, however, exploit new opportunities to advance algorithms for smartphone positioning. First, we have access to carrier phase measurements since the introduction of the new API since 2006. We also have access to multi-constellation and multi-frequency capabilities. And lastly, we have access to raw GNSS measurements via open source tools. Let us look at some of the prior approaches that have tried to address the Google smartphone Decimeter challenge. On one hand, we have model-based approaches such as factor graph approach that tries to jointly optimize for position and velocity. This was actually the winning approach for both 2020 and 2021 years. Some prior works have also looked at trying to design an extended Kalman filter by tightly fusing GNSS with other sensors such as IMU and magnetometer. Some people have also tried to apply post-processing methods such as PPP to improve the positioning accuracy. On the other extreme, we have learning-based methods where some prior works have tried to explore regression type of techniques such as linear and Bayesian ridge regression, or attention-based neural network that tries to learn positioning correction in an end-to-end manner. There's also one notable work that tried to utilize a hybrid approach. Specifically, this work used a Kalman filter to couple GNSS with IMU measurements and used reinforcement learning to adaptively tune the noise covariance. Some of the pros of model-based methods are that so far, these methods have shown to have high positioning accuracy on the Decimeter challenge datasets. They also have faster runtime and faster convergence. However, they need a lot of covariance tuning as well as accurate assumptions on the noise models. Learning-based methods, on the other hand, make less assumptions about the underlying data structure while being more robust and fault-tolerant to uncertain noise models. They are, however, sensitive to initialization and feature design, and so far have not been able to outperform model-based methods. In this work, we propose a hybrid framework to try to learn positioning corrections from smartphone measurements. Our work uses a model-based approach, which makes use of temporal information, and also a learning-based approach, which is a snapshot positioning technique. From the model-based approach, we utilize the initial position as well as preconditioned inputs that are then fed to the learning-based approach. The learning-based approach then refines the initial position correction and applies it to the position from the model-based approach to infer the final smartphone receiver position. Our contributions are as follows. We propose a hybrid framework using model-based and learning-based methods to learn position corrections. For learning-based approach, we design a graph convolutional neural network that can represent different graph structures. We use a Kalman filter for better initialization of the GCNN and to condition the input features. Lastly, we evaluate a proposed approach on real-world datasets collected in urban environments. Here's an outline of my talk. I'll first talk about the proposed algorithm and go over its different components. Then I'll talk about the experimental setup and real-world evaluation on urban datasets. And finally, I'll conclude my talk. The choice of model-based approach in our work is the Kalman filter. This is because it uses temporal history of GNSS measurements, converges quickly, and is also computationally efficient over other filtering methods. For our state, we choose to track both the 3D position and the 3D velocity. Tracking velocity jointly in the state space improves positioning performance. Finally, we use the estimated position to condition the inputs for a learning-based approach. The choice of learning-based approach in this work is the graph convolution neural networks, or GCNN. This is because factor graph optimization was the winning approach of the 2020 and 2021 Decimeter challenge. This is encouraging because we can make the GCNN learn such a graph by using satellite positions as nodes and preconditioned inputs from the Kalman filter. GCNN is also capable of handling varying satellite visibility in urban environment and making use of measurements from multiple constellations and multiple signal frequencies in the same graph. Next, I would like to give a brief background about GCNN. The idea is that they apply convolution operations on a graph with inputs, such as nodes V and edges E, a feature matrix X that contains the graph signal on each node, and an adjacency matrix A that describes node connections. In this matrix, an element is 1 if two nodes are connected and 0 otherwise. The convolution filter parameters remain the same for all nodes, and then we try to learn the weights for each layer using differentiable propagation rule. Here is a sample GCNN architecture that takes in an input graph signal, applies 2 layers of graph convolutions, and then a fully connected layer to infer a graph level output. Here is a sample feature matrix X and a sample adjacency matrix A. The GCNN is able to learn and distinguish between different graph structures. Different graph structures are dictated by what is known as graph isomorphism. Two graphs are known to be isomorphic if there exists a mapping that preserves the node and the node adjacency in both the graphs. An example isomorphic graph pair is shown on the right. A classical method to check graph isomorphism is the WL test. Only some convolution layers can satisfy the WL test and can therefore model different graph structures. Our design choice of the graph convolutional operator in this work is the GIN-conv, since it is able to satisfy the WL test and therefore can be powerful at distinguishing between different graph structures. Next, I would like to talk about the feature preprocessing module, where we start from raw measurements from the GNSS logger app. We then group them by their constellation and signal type. We eliminate errors such as inter-system and interfrequency biases, clock biases, tropospheric and ionospheric errors. We apply ADR smoothing or Doppler depending on if there is a presence or absence of cycle slip. And then we infer the final feature vector. Using this feature vector, we can then construct a feature matrix. The feature matrix contains feature vector for every satellite in the graph, which is essentially concatenated loss vectors and range residuals. These are constructed using the initial position estimate from the Kalman filter. As an example, you can see a sample single layer graph here, where different measurements are grouped according to GPS, Galileo, and GLONASS. A sample feature vector for a node looks something like this, where the first 3 elements represent the loss vector, and the last element represents the measurement residual. If we combine the feature vectors for every single satellite node, we end up with this sample feature matrix. As an example here, you can see a feature matrix for the GPS cluster. Similarly, we design an adjacency matrix that connects satellites if they are in the same constellation, or satellites from different constellations if they have similar measurement residuals. As an example, you can see that a node in the GPS constellation has the feature vector as shown here, with the measurement residual being 15, and a node in the Galileo cluster has a feature vector here with a measurement residual of 18. Because the difference in these residuals are less than 5 meters, we decide to connect both the nodes even though they belong to different constellations. And this is important because design of the adjacency matrix helps leverage multi-constellation measurements. Otherwise, the GCNN ends up being a fully connected network and loses discriminative power or the ability to distinguish between different graph structures. Here is a sample adjacency matrix for the entire cluster. Next, we move on to the design of convolution layers. As mentioned previously, we design GI and conv layers that update node features iteratively by aggregating feature vectors of nearest neighbors and can also effectively distinguish between different graph structures. Here is a sample example of how the GI and conv layer operates. If we assume that the feature vectors of a node's neighbors form a multi-set or a set containing repeated elements, then the aggregation operation in the GI and conv layer can be thought of as an aggregation operation over the entire multi-set. Next, we move on to the pooling and prediction layers. Pooling in the GCNN helps instantiate message passing among different nodes and exchanging information. There are many choices of pooling, but we decide to use mean pooling, which essentially averages node predictions and reduces the spatial resolution of the graph for subsequent layers, such as a fully connected network. Post-message passing, we design multiple linear layers that help increase the graph expressivity before we perform our final prediction. The final prediction for our work is the position correction, which is a 3x1 vector. Here is a summary of the overall algorithm. To summarize, we start from the model-based approach, which is a Kalman filter that provides both initialization to the GCNN as well as conditioned input features, which are then passed through the feature preprocessing module. And lastly, we have the learning-based approach using GCNN that takes in a feature matrix, an adjacency matrix, and then provides a position correction that we then add to the initial position learned from the Kalman filter to end up with the predicted position. Next, I would like to talk about experimental evaluation on real-world urban data sets. For this work, we chose to evaluate our algorithm on the Google Smartphone Decimeter Challenge 2021 datasets that are collected in multiple cities as shown in the right. The GNSS measurements are collected from Android smartphone receivers, and the ground truth is collected from a Novotel span system. Here is a sample trajectory from San Jose, which comprises a part of the training dataset. As baselines, we choose to evaluate our approach against a weighted least square solution, which is a snapshot approach, and a Kalman filter solution, which is a temporal approach. Note that we tune both the baselines using Bayesian hyperparameter optimization to achieve maximum possible performance and to stress test our approach. For metrics, we use quantitative metrics such as the mean, median, maximum, and minimum horizontal positioning error. We also study the distribution of positioning error. Qualitatively, we observe the trajectory tracking with respect to ground truth. Here are some of the key experimental parameters. We use about 81 training datasets and then test our approach on 17 test datasets. Note that some of these test datasets include new cities that are absent from the training dataset, with Los Angeles being an example. We train our approach for about 100 epochs using a mean square error loss function and Adam as the optimizer. We trained and tested our approach using multiple hardware platforms and multiple accelerators. The design of the GCNN and the entire learning-based approach was done using the PyTorch geometric library. Some of the key GCNN parameters are listed on the right for your reference. Here is a summary of the positioning error on test datasets. As shown here in the table, our approach has the highest positioning accuracy since it has the lowest mean error, median error, minimum error, as well as maximum error. This shows that our algorithm outperforms both the WLS and the Kalman filter baselines across all 17 unseen test datasets with respect to every single metric. Here is a sample horizontal positioning error distribution on one of the test datasets. As shown in the graphs, you can observe that our approach has few outliers, which is defined to be errors that are higher than 5 meters, and is able to provide more accurate positioning compared to the Kalman filter baseline. Note that we only show the error distribution for the Kalman filter baseline since it generally outperforms the WLS baseline for all of the test datasets. Moving on, we show the error distribution for another dataset. For this dataset, we chose the LA one because this forms a part of the test dataset and was not a part of any of the training datasets that were used to train our GCNN. Again, as shown here, our approach has fewer outliers and provides more accurate positioning even in unseen cities such as LA. Finally, we show qualitatively the positioning accuracy when compared against ground truth. For this, we use the validation dataset of Mountain View. And then as you can see here, compared to the Kalman filter baseline, which are the plots shown in orange, our approach, which are the plots shown in yellow, is able to outperform the Kalman filter baseline as well as track the ground truth trajectory more closer. Here are some of the magnified versions that show both the Kalman filter approach and our algorithm approach and the effect on the positioning accuracy. Thus, our approach follows ground truth more closely compared to the Kalman filter position. To conclude our talk, we designed a hybrid framework using model-based and learning-based methods to learn position corrections. For learning-based approach, we designed a GCNN to aggregate measurements across multiple constellations and multiple frequencies. For better initialization of the GCNN, we constructed features using position estimate from a Kalman filter. And lastly, we evaluated our approach on real-world datasets collected in urban environments and outperformed model-based approaches in terms of positioning error. I would like to acknowledge Google for making available such a large amount of datasets for 2020 and 2021 years, as well as Zach, Nikhil, Shubh, Ramya, and the rest of NavLab members for their insightful discussions. Thank you.